Hello everyone, welcome to Enviro Pioneers. This video is about the interaction of electromagnetic radiation in atmosphere. Atmosphere, it plays a very important role in the propagation of the electromagnetic radiation. So this video is made to understand the concept of different phenomena that occurs in atmosphere and why the understanding of this interaction is important in remote sensing. So as we discussed in the last video, that remote sensing process is the acquisition of data about the Earth's surface features with the help of the non-contact sensors, and these sensors they record the reflected and the emitted energy from the Earth. So before reaching to the sensor, the electromagnetic radiation coming from the source, they have to travel twice through the Earth atmosphere. Once when they are coming from the sun towards the Earth, and second when they are getting reflected or being emitted. So the second time interaction that depends upon the altitude of the sensors. If the sensors are placed near to the Earth surface, the second time interaction will be less, but if the sensors are placed on the aerial vehicle or on the satellite, the second time interaction will also play very important role. So this atmosphere, it affects the propagation of electromagnetic radiation in many ways, which we are going to see in the further part of the video. So when this radiation, it travels through the atmosphere, there is gradual reduction in its intensity. So this reduction in intensity with distance in medium, this is called attenuation of light. So the attenuation of electromagnetic radiation in the atmosphere, it occurs mainly because of the scattering and the absorption of the radiation in the atmosphere. This image, it represents overall atmospheric propagation effects. There may be gaseous molecules, clouds, aerosols, particulate matter, water molecules, water droplets. So depending upon the composition of the atmosphere at a particular place, there may be scattering, absorption, reflection, or the transmission through the cloud. So these overall affect the incoming solar radiation as well as the outgoing radiation. This image, it represents different type of phenomena that occurs when a wave travels in a medium. There may be transmission, reflection, refraction, diffraction, absorption and scattering. So here we can see that from the source, when the electromagnetic radiation is moving through the atmosphere, some portion is absorbed, some portion get scattered because of the reflection and the refraction process. Then some crosses through the medium to reach the Earth surface, that is the transmission, and on the clouds we can see the scattering. And here this part, the second half, it is representing the outgoing radiation. So outgoing radiation again, when before reaching to the sensors, it can get scattered or absorption may occur, and same may occur with the emitted radiation. So overall there is three process: absorption, scattering and the reflection. But also there is one more: refraction. So here one term is mentioned, the path radiance. So that is the radiation that has been scattered in the Earth atmosphere and which reach to the sensor without contacting the Earth surface. Means इलेक्ट्रोमैग्नेटिक रेडिएशन का वो पार्ट जो अर्थ सरफेस तक नहीं आता बट फिर भी सेंसर तक पहुंच रहा है, that may be after reflection or scattering. So the part of the radiation that is reaching to the sensor without contacting the Earth surface, that is referred as the path radiance. So in our atmosphere, four major phenomena that occur are reflection, refraction, scattering and absorption. In the energy budget video, we saw that overall reflection from the atmosphere is 26%, that is 20% from the cloud and 6% from the other atmospheric component. Now in this video, we will be discussing about the atmospheric refraction, scattering and absorption. Refraction, is the process when there is deviation of the wave from the straight line when it comes across the change in the medium or variation in the density. So atmospheric refraction, it refers to the deviation of the electromagnetic wave when it passes through the atmosphere and it comes across the variation in the air density with altitude. This atmospheric refraction is a function of the temperature, pressure and humidity. This is minimum when the sun is overhead and maximum when sun is at the horizon. Because of atmospheric refraction, the actual position of the celestial object seems to vary, as well as the visual appearance of the sun varies as per the atmospheric condition. Here we have the normal sunset, but when there is inversion condition, inversion is increase in temperature with height, that is the reverse of the normal atmospheric condition. So that term is inversion. Here we have the four condition: warmer surface than the overlying air, weak inversion above the eye level, strong inversion below the eye level, strong inversion at eye level. So depending upon the height at which inversion occurs and in how much intensity, the visual appearance of the sun seems to changes. Next is scattering. Scattering is a process in which the electromagnetic radiation, it interacts with atmospheric component, that may be particle or the large gas molecules, and then get redirected in all the directions from the original path. So it is different from the reflection because in scattering, the direction in which it will be scattered, that is unpredictable, while in the case of reflection it is predictable. This scattering, it depends on several factors such as the wavelength of the radiation, then the abundance of the particles or the gases and their size, and the distance the radiation has to travel through the atmosphere. Now, on the basis of size of the particle or the atmospheric component and the wavelength of the electromagnetic radiation, scattering, it may be classified into two types: selective and the non-selective. Selective scattering means that scattering is selective for particular wavelength range. Generally, shorter wavelengths are scattered more in comparison to the longer wavelength. And non-selective means scattering is uniform for all wavelength range. Now this selective scattering is again classified into Rayleigh scattering and Mie scattering. So here we can see the difference between these three. So here we have any atmospheric component, when light is incident on it, the light is getting scattered. So the difference is on the basis of size of the particle on which this light is incident and the pattern of scattering. So this is representation of an electromagnetic wave. So distance between two successive crests or two successive trough or two successive starting point is referred as the wavelength. So wavelength, it is generally given in micrometer, nanometer. So, if we compare the size of the atmospheric component with the wavelength of the electromagnetic radiation, we have different type of scattering. So, Rayleigh scattering is when the size or effective diameter of the component or the particle, it is very less in comparison to the wavelength of the incident radiation. Means if the size of this component is very less in comparison to the wavelength of incident light, in that case we have the Rayleigh scattering. So this mainly occurs when the light is incident on the gaseous molecule. And second is Mie scattering. Mie scattering, when the size of this atmospheric component is equal to the wavelength of the incident radiation, and it mainly occurs when the light is incident on the smoke particles or dust particles. So that scattering is referred as the Mie scattering. Non-selective scattering, it is mainly when the size of the atmospheric component is much larger than the wavelength of the incident radiation, then in that case it is non-selective scattering. And it mainly occurs when we have the presence of water vapor in the atmosphere. And second difference is the pattern of scattering. So here we can see that this is the direction of incident light. So when light is incident on the gaseous molecule, scattering it is uniform in all the directions. While in case of Mie scattering, when the light is incident on the dust particle or the smoke, we have more scattering in the forward direction and it is spread out. And in the back direction, we are having the less scattering. While when we come to the non-selective scattering, again, this is similar to Mie scattering, but the scattering is narrowed down in the forward direction. In relay scattering, we have the uniform scattering in all the direction, while in the case of Mie and the non-selective scattering, we are having more scattering in the direction of incident light in comparison to the opposite direction. Rayleigh and Mie scattering are the selective scattering. Selective scattering means they are selective for particular wavelength range. Here we can see that the intensity of scattering is inversely proportional to the lambda 4. Lambda is the wavelength. It means shorter is the wavelength, more will be the scattering. This diagram is a plot of percent scattering of direct sunlight against wavelength in nanometer. So this is for the visible radiation and starting from 400 nanometer to 650 nanometer. So we can see that amount of scattering for the blue wavelength is much higher in comparison to the red one. When we look at our sky, we observe different colors. Sometimes it is sky blue, sometimes it is reddish orange, sometimes it is orange, yellowish orange. So these colors, it depends mainly upon the Rayleigh scattering and the position of sun with respect to earth. When sun is present overhead, sun rays has to travel lesser distance in the atmosphere, and during its path the blue wavelength is scattered more in comparison to the other wavelength, giving the blue visual appearance to sky. But at the time of sunrise and sunset, when the sun is present at the horizon, the electromagnetic radiation or the sun rays has to travel much larger distance, and because of the increase in its path, the blue light is scattered in the upper atmosphere itself, and the only wavelength which reach to the earth are the longer ones, which is red, orange and yellow, giving the different beautiful colors to the sky. Then next is Mie scattering and the non-selective scattering. Mie scattering is also selective scattering where it is inversely proportional to 1 by lambda square, and it mainly occurs when the light is incident on the water vapor or the dust particles, and here shorter wavelength will be scattered more in comparison to the longer wavelength, but the pattern of scattering is different. Here the scattering is more in the forward direction in comparison to the Rayleigh scattering. So Mie scattering is responsible for this glazy appearance around the sun or in the sky. So in the case of the polluted atmosphere, या फिर smoke है या dust particles ज़्यादा हैं, in that case, when sun rays are incident on those particles, it gives white hazy appearance in around the sun or in the sky. So in general, Rayleigh scattering and Mie scattering are responsible for different colors of our sky. Then we have the non-selective scattering. So this is mainly when the diameter of the particle is much larger than the wavelength of the incident radiation, and it is non-selective with respect to the wavelength. It means within the visible range, all the wavelength will be scattered in equal amount and in the forward direction. So if there is presence of cloud in the sky and when light is incident on it, all the wavelength are scattered in equal amount in the forward direction, and because of that these clouds appear to be white to us. So next is atmospheric absorption. Absorption means when the atmospheric component they absorb the electromagnetic radiation. So here we have the electromagnetic spectrum starting from the cosmic rays to the radio waves. So this is in the increasing order of wavelength and decreasing frequency range. So here mainly the cosmic rays, gamma rays and the X-rays, these are absorbed in the upper atmosphere itself, and the portion which we receive from the sun is the ultraviolet, visible and the near infrared. Atmospheric absorption, it can be represented in two ways, either percentage absorption or percentage transmission. Absorption and transmission both are reciprocal. If we are having more absorption, it means less transmittance, and if it is less absorption, it means more transmittance. In this diagram, here we have the different wavelength range and the percentage absorption. The ultraviolet, visible, near infrared, then infrared. In our atmosphere, some of the gaseous molecule and the water vapor they absorb the electromagnetic radiation. बट जो ये एब्जॉर्बेंस है वो पर्टिकुलर वेवलेंथ रेंज में होता है. यहाँ पे अगर हम एग्जांपल्स देखें, यहाँ नाइट्रस ऑक्साइड, मीथेन, ऑक्सीजन एंड ओजोन, कार्बन डाइऑक्साइड. सो नाइट्रस ऑक्साइड इट इज हैविंग द एब्जॉर्प्शन पीक इन द मिड वेव इंफ्रारेड and then near to the long wave infrared and a smaller peak in the very long wave infrared. Then methane, it is having mid wave infrared and then again here near to the long wave infrared. Then in oxygen and ozone, most of the absorption peak it is in the ultraviolet portion, but if there is tropospheric ozone we have in the infrared portion also. Then carbon dioxide, it is having the absorption peak in the shortwave infrared, then one peak in between, and then here we have in the midwave infrared portion and then very long wave infrared portion. So likewise अगर हम water vapor का देखें, so it is having many of the absorption peak, means it is responsible for the absorption of the electromagnetic radiation in the NIR, shortwave infrared, midwave infrared, and then here also in this portion means the wavelength range in between midwave and the long wave infrared. यहाँ पे भी इसका peak है and then very long wave infrared portion is also getting absorbed. So this is component wise, but if we talk about the total atmosphere, so ये हो गया हमारा total absorption. Means if we are talking about the incoming and the outgoing radiation, much of the radiation is absorbed in the atmosphere itself. यहाँ ultraviolet portion में हो गया, visible we are having no absorption, but in the near infrared we are having many absorption peaks. ये जो absorption peaks हैं, they represent those wavelength range where the electromagnetic radiation is completely absorbed in the atmosphere. So opposite of the absorption is the transmission. It means wherever we are having the more absorption, there will be having the less transmission. Transmission is the passage of the electromagnetic radiation through the atmosphere. यहाँ पे अगर आप देखो ये विजिबल में हमारा परसेंटेज एब्जॉर्प्शन कम था, बट हियर वी आर हैविंग दी near to the 100%. And then likewise in the reflective infrared and the thermal infrared we are having the wavelength ranges where we are having the more transmission in comparison to the other wavelength ranges. Of the electromagnetic spectrum, there are very selective wavelength ranges which are not getting absorbed in the atmosphere या फिर जो atmosphere में transmit हो रहे हैं without much interference. तो वो जो wavelength range है उसको हम कहते हैं atmospheric window. So atmospheric window is defined as the wavelength range in the electromagnetic spectrum that can pass through the Earth's atmosphere with minimum absorption. तो अगर हम पैसिव रिमोट सेंसिंग के लिए देखें, so we have three windows: visible window, infrared window, and then microwave window. For radio waves, our atmosphere is completely transparent, and इसी वजह से हम इसको radar में use करते हैं because the radio waves which is transmitted from the platform, it will reach to the earth surface and without much interference, it will be detected back by the sensor at the platform. So why this atmospheric window is important in remote sensing? As we discussed, this remote sensing, it mainly works with the help of non-contact sensors which detect the reflected and emitted signal. So जो sensors ये platforms पे place किए जाते हैं, they are designed in such a way that they are sensitive for the wavelength range which falls in the atmospheric window. क्योंकि अगर हम वैसे सेंसर्स डिजाइन कर रहे हैं जो ये पर्टिकुलर वेवलेंथ रेंज के लिए सेंसिटिव है, सो दैट विल नॉट बी यूजफुल, क्योंकि ये जो सिग्नल है या ये वेवलेंथ रेंज जो है वो एटमॉस्फेयर में एब्जॉर्ब हो जा रहे हैं एंड सेंसर्स तक नहीं पहुंचेंगे. तो हमें ऐसे वेवलेंथ रेंज सिलेक्ट करने हैं जो एटमॉस्फेयर में कम से कम एब्जॉर्ब हो रहे हैं और ज्यादा से ज्यादा ट्रांसमिट हो रहे हैं, सो दैट इफ द सेंसर्स आर प्लेस्ड ऑन द एरियल व्हीकल और ऑन द सैटेलाइट, these sensors can detect that particular wavelength or particular signal coming from the earth. So here again it is summarized that if we are talking about the gamma rays, X-rays and ultraviolet light, it is blocked by the upper atmosphere. Visible light जो है that reaches to the upper atmosphere. Most of the infrared spectrum is absorbed by the atmospheric gases. Then radio waves, it can be detected from the earth, but the long wavelength radio waves are blocked. This image, it is a summary of shortwave radiation and the long wave radiation emitted by the sun and the earth. Then here we have the wavelength range which are transmitted or absorbed in the atmosphere, and on the basis of these atmospheric window we can have the different type of remote sensing system. Human eye, it can work only in the visible range, but the photography, here we can utilize some portion of ultraviolet, visible and the near infrared. Then for the long wave infrared, we have the thermal IR scanners. Then we have the electro-optical sensors which are designed to detect the signal from ultraviolet, visible, near infrared and thermal infrared. Then we have the passive microwave and the imaging radar, and in this also we can utilize this particular atmospheric window. So passive microwave remote sensing utilize the emitted radiation, while in imaging radar we illuminate the area with the radio signal and then detect the backscattered signal. I have taken the help of this chapter available on the website along with the content from the book Remote Sensing of Environment. If you have any question, please drop in the comment section. Thank you all.